Hello everyone, this is Dr. Anandan, Assistant Professor in Physics, Dr. N.G.P Arts and Science College. Today I am going to talk about cadmium telluride solar cells, and this is coming under the course of photovoltaic science. So in this video I am going to show the introduction to cadmium telluride material and the properties of cadmium telluride and some of the deposition techniques which is used for cadmium telluride thin films. Generally, solar cells can be classified into three generations. The first generation, which means is a silicon-based solar cells. So we have monocrystalline wafer-based silicons and similarly polycrystalline silicon solar cells. These are all coming under the category of first generation solar cells. And second generation solar cells, these are all based on thin film based solar cells. For example, amorphous silicon and cadmium telluride. Similarly, CAGS based thin films are coming under the category of second generation thin films. The modern third generation new emerging technology based solar cells are like nanocrystal based solar cells, polymer based solar cells, dye sensitized DSSC, dye sensitized based solar cells, then concentrated solar cells, multi-junction perovskite based solar cells. So these are all actually third generation solar cells. So this cadmium telluride solar cell is coming into the category of the second generation thin film based solar cells. So this is the crystal structure of cadmium telluride, which is a zinc blende structure. This is arrived by making a second and sixth group combination of materials. That is, cadmium is from second group and tellurium is from sixth group element, and it's a compound semiconductor. And the value of band gap value of this CdTe is coming around 1.5 electron volts. This is ideal for utilization of AM, the Yermas index 1.5 radiation completely. And since it is a compound material, this is a direct band gap material, and it is having very high absorption coefficient greater than 10^5 centimeter inverse, and the band gap value can be altered by substituting the tellurium material, and it is having the structure of zinc blende structure, which is a very the covalent band like a silicon structure, and can be made both. We can make a cadmium telluride by both material, like a P-type material as well as N-type material, by changing the contents of the stoichiometry, and it is optimum values for flexible type solar cells, because it's a thin film technology. We can use this material for a flexible type solar cells, and it is also used for infrared optical window and all the similar like purpose. So this is the structure for cadmium telluride solar cells. It is a superstate type solar cell, which means the light enters into the glass side, and the next layer is the first layer is actually TCO, transparent conducting oxide. It's made by either ITO or Zn zinc aluminum doped zinc oxide, or some CTOs. So either one of TCOs, and the next layer will be window layer. Window layer means it is a N layer. Yeah, N-type layer. That is mostly they use a cadmium sulfide. Then absorption layer, cadmium telluride, the main absorber. The next one, the back conduct, mercury telluride, copper doped mercury telluride. Here it is used, but it's a typical example for a CdTe solar cell. Okay, there are different structures are there. Not only this back conduct, there are some other back conduct also used. And finally, the electrode. That is a silver based electrodes are there. Some other electrodes also used. Okay. So here you can see the panels as well as the flexible type material. It's a polymer based substrate. This is a flexible substrate it is used. So This is the basic structure of the absorption coefficient of this cadmium telluride. So it is the graph is compared with other potential candidates like the germanium. So this is actually the dotted line gives the actual efficiency curve. Okay, it is compared the solar cell efficiency dotted line for AM 1.5 is given as a dotted line here. So 100 milliwatts per centimeter square is given here. So the other values are compared here. The germanium is coming under some 0.7 electron volts, and similarly gallium arsenide coming under 1.3, and cadmium telluride 1.5, and cadmium sulfide that is 2.4. These are all the band gaps, and it is also showing the absorption coefficient, how where it is getting absorbed after in 1.5 it is coming around so nearly more than 24.5 above this level. So the maximum efficiency versus band gap is it's a trade-off between current and voltage. So lower the band gap, you will get a higher the current. At the same time, higher the band gap, you will get a lower the voltage. So VOC is linked to this the band gap value. So here the cadmium telluride, the value is 1.5 electron volts. So this actually uses the, because you can see that the first diagram, the efficiency percentage diagram, you can see that indium phosphide, then gallium arsenide, then here you can see the cadmium telluride. So the cadmium telluride has the nearby the maximum value of this efficiency. You can obtain the maximum efficiency of the CAM 1.5 spectrum of the sun. So this is the advantage of this cadmium telluride solar cells. So compared to silicon, so the silicon technology is so expensive because of its purification cost, controlled doping, okay, and we need to get a wafers technology, then that has to be cut it down, and it has to be polished. So many things are there in silicon. Whereas cadmium telluride is a direct band gap material, but silicon is indirect band gap material. Okay, so that it has a huge absorption coefficient. So very small thickness is enough to absorb a huge amount of sunlight. So that is the first advantage of this cadmium telluride solar cells. And the making of cadmium telluride is also comparatively very cheap with the silicon. Okay, so these are all the advantages of cadmium telluride. And the main important disadvantage is cadmium safety. I mean cadmium poison. Or they used to say that the cadmium is a heavy metal, and it is toxic to the human body. But whereas what will happen in the real case, so these are all the emissions are given in one study. So here you can see that where this cadmium telluride is coming into. So the cadmium telluride is 0.3% compared to oil and nuclear, the other um, carbon emissions. Okay, so 99.5% cadmium remained in a module, and the loss was through ends of exposed ends of module, and in the real world modules loss expected to be 0.04%. So this study gives some study gives the cadmium telluride can be further utilized in the module, and these are all the it shows the properties of cadmium telluride material. So it has an optical band gap of 1.5 electron volts at room temperature, and you can additionally add some sulfur, and you can modify the band gap value. Here it is modified by some 0.05 is added, so which means it's a 5% added sulfur added to the cadmium telluride. So here it is changed to 1.47 electron volts. So the temperature dependence of Eg, that is the band gap, the rate of change of band gap with respect to Eg is equal to rate of change of temperature. I mean rate of change of band gap with respect to temperature is 0.4 minus 0.4 milli electron volt per Kelvin. So electron affinity is given as a 4.28 electron volts, and the important point is the absorbing coefficient is greater than 5 into 10 to the power 5 per centimeter. And some another important factor is the mobilities. You can see the mobility which is used for solar cell applications. And these are all the phase diagram of cadmium telluride. So this bottom shows it's a liquid phase, sorry, it is a solid phase, and the top one is showing the liquid phase. So here you see that it is atomic percentage of tellurium, which means if tellurium is 0, which means it's a completely cadmium. The cadmium is starting at 600 something, some 700 degrees centigrade. Similarly, for tellurium, melting point is around some nearly 450 something. But whereas the cadmium telluride is going to up to 1092 degree centigrade. It's a very high value. Combined together, cadmium and telluride combined together and makes a very high melting point. Okay, so this is given here, and the second graph gives the vapor solid uh, versus 1 by T diagram, which means when the temperature lows, I mean the temperature lows and the pressure also get decreased, so that you can see that where we can get the material. So it is comparatively given for cadmium sulfide and cadmium telluride, cadmium chloride and tellurium and cadmium, all those things it's compared. So this line if you follow, then we can have a cadmium telluride thin films at the required pressure level and the temperature level. And so some of the cadmium telluride deposition techniques are given in this picture. The first one is actually closed place sublimation. So which means the substrate, the dot, the line, the rectangle is actually substrate, and there is a substrate heater here. It is given. So this is heated up to some 600 degrees centigrade, and the cadmium telluride material is taken, and it is heated up to 650 to 750 degrees centigrade, and the thickness will be getting around 1 to 15 micrometer at the rate of 1.5 micrometer per minute. So the growth rate will be 1.5 micron per minute. So this is how you can quote this cadmium telluride by closed space sublimation technique. So the pressure used in this technique will be around some 10 tar. The second technique will be used for this cadmium telluride is vapor transport deposition. So in this deposition, you can see that the substrate is kept here underneath, and with 600 degrees centigrade, and there is a carrier gas. The carrier gas will be usually the inner gas will be taken, and there is a heater here, and it is heated up to 700 degrees centigrade, and finally you will get the deposition of cadmium telluride material as a in the substrate. And the pressure level used was 10 to 100 tar range, and the thickness will be usually getting from this particular material is 1 to 10 micrometer, and the growth speed is 0.1 to 1 micrometer per minute. And the third technique is used for this cadmium telluride deposition technique is physical vapor deposition. This is generally used in most of the cases. Here there is any filament or boat will be there. So in the boat you will have a solid cadmium telluride material, and it is heated up to 700 to 900 degrees centigrade with a pressure of 10 to the power minus 6 tar, and the substrate will be kept at 400 degrees centigrade. Then you will get this cadmium telluride uniform coating here, and the growth rate will be around 0.01 to 0.5 micrometer per minute. It is a very controlled way of coating, and the thickness will be obtained by this method is 1 to 5 micron to obtain the required absorption coefficient of this, required cadmium telluride material. Similarly, in the sputter deposition, so the sputter, the pressure will be around 10 to the power minus 4 tar, which means there will be a argon or some inert gas will be there, sputtering gas, and the cadmium telluride target will be there as it is acting as a cathode, and there will be a huge potential will be given between this anode and cathode. So here anode will be kept near the substrate, and it is also heated up to some 200 degrees centigrade. There is a filament is given here, and So when we give the potential between anode and cathode, the electrons will, the argon ions will ejected out this cadmium telluride material, and it will be coated on the substrate. And the thickness will be around 1 to 4 micrometer, and at the rate of 0.1 micrometer per minute. Similarly, the fifth method for deposition of cadmium telluride is electrode deposition. So here there will be electrolyte will be there. In the presence of electrolyte, then there will be a one will be actually the platinum or some anode will be there, and in the cathode you will have a substrate and the cadmium telluride, uh, and with the hydrogenated telluride material will be there, so that you will heat it up to some 80 degrees centigrade. And these are all the atmospheric condition growth methods, these four. So so the thickness will be around 1 to 2 micrometer at the rate of 0.01 to 0.1 micrometer per minute by the electrode deposition method. Similarly, the another method is metal organic chemical vapor deposition. So in this method, you will have a chemical vapor will be there. There will be a reaction, and the reaction chemical reaction will yield the cadmium telluride vapor, and with that there will be a um, there will be the gas, the final gas output will be coming into the substrate, and it will be deposited here. The substrate also will be kept at the temperature of 200 to 400 degrees centigrade. So the thickness value will be around 1 to 4 micrometers at the rate of 0.01 to 0.1 micrometer per minute. So this is the sixth technique. And similarly, the seventh technique will be spray deposition, spray pyrolysis. So in this technique, we will use a cadmium chloride plus telluride, so tellurium material, and as a mixture, and they will send it to high pressure to the substrate. The substrate will be kept under temperature of 600 degrees centigrade, but it is in at 1 atmospheric, which means atmospheric conditions it is done. So the thickness will be around 1 to 20 micrometers. You can get it, and at the rate of 1 micrometer per minute. It is a little bit faster deposition. And the next one is screen print deposition. So here you will have a cadmium telluride slurry. It is a little semi-solid. So here you will have a screen, and you have a low temperature. Here you have to keep a substrate at very low temperature, minus 25 degrees centigrade, and then the slurry will be moved here and there and in the screen, so that you will get a screen print of a cadmium telluride material. So you can get a thickness of up to 5 to 13 micrometer. So these are all the 8 important techniques for cadmium telluride deposition. And there are a few additional layers, the functional layers that we have seen already in a first slide. The structure of cadmium telluride solar cells. So one important layer is window layer. So window layer here is cadmium sulfide here. So cadmium sulfide material is used as a window layer, and the band gap of 2.4 electron volts that we have seen in the first slide itself, the comparison graph. So this is a N-type window layer. So which means that cadmium telluride is acting as a P-type layer, and this CDS is acting as a N-type layer. And typically the thickness will be 60 to 300 nanometer, and there will be a depletion region resides within the cadmium telluride, plus carriers will generate the CDS to recombine. So that is the idea, so that you will have a huge thickness of cadmium telluride. So it will absorb a huge amount of light, and it will generate a minority carrier, that is electrons, and there will be a recombination, and there will be the depletion region between the cadmium sulfide and the cadmium telluride, so that you will get the potential difference. With that, it will be splitted away the electron hole pairs, and finally you will get the output of the electrons, which means as a potential and current. So you can make a desirable thickness of cadmium sulfide material, and that changes the short circuit current. This is very important to grow the cadmium sulfide thickness, that varies the short circuit current. And it can be prepared by chemical bath, RF sputtering, and the closed space sublimations. So these are all the technique of cadmium sulfide material growth. Another important material is transparent conducting oxide layer. That is actually coming as one of the electrode uh, that actually sitting near the cadmium sulfide. So, so the transparency should be greater than 85% so that it can allow maximum number of photons inside the solar cell. And sheet resistance will be less than 10 ohms per square inch or square centimeter. So which means that allows the very small sheet resistance means it can able to have a huge number of electrons density, and it should be also stable. That means when time goes up, you should not get degraded. So these are all the commonly available transparent conducting oxides like ITO, that is indium tin oxide, and ZaO, which means ZnO doped with aluminum, and similarly cadmium tin oxide, CtO. So these are all the three transparent oxides which is used for mainly this cadmium telluride solar cell material. So, so in this video, we have seen the various properties of cadmium telluride material, which means we have seen how the optical band gap is compared with other materials, potential materials, and what is the importance of this cadmium telluride compared to silicon technology, and what are the deposition techniques available for CdTe thin films. Okay, so there are 8 methods we have seen. It's a schematic diagram, but it has explained all. And we have also seen what are the additional layers required for this solar cells, and the complete solar cell can be used uh, for many applications. It's a flexible solar cell also. Okay, so with that, so we'll see we have seen the cadmium telluride solar cell, the function of cadmium telluride solar cells. Okay, thank you very much. Thank you so much.